Hello, everyone. Today we are going to continue with integrals. Just like always, I'm going to give you some questions and you should think about them for a few minutes. And after that, I would solve them for you. So it's best if you have your paper and with your pen with yourself. And now I'm going to start to write the questions for you. Okay, so let's start. The first question. So most of the questions, they focus on integral today. The first question is about the function f from the interval 0, 1 to r. Suppose we have a function from the unit interval to r, such that we know the function f is integrable on the closed interval b to 1 for any b, a number between 0 and 1. Okay. Does it mean that f is integrable over the integral 0, 1? That's the question. If it's integrable over this smaller interval from b to 1 for any b between 0 and 1, does it imply that f is integrable over the whole integral 0 to 1 or not? So either you should prove it. So either if you think the answer is yes, you should prove it. If you think the answer is no, you should find a counterexample. An example of a function f where the function is integrable over any interval of this form, b to 1, but it's not integrable over the whole integral 0 to 1. Okay, think about it for a few minutes. Okay, what do you think? Do you think the answer is yes or no? Okay, yeah, we have a good counterexample. So if we take f of x, the function f of x, yes, both of you, yeah, that is correct. Yeah. So if we take f of x to be 1 over x, it's a function defined on the open interval, but well, the interval which is open from the left side and it's closed on the right side too. So this is still not a correct counterexample because f is not defined at 0. So we can just formally define f at 0 anything we want. So we can say, for example, if x is in the interval 0 to 1, open interval from the left side, half open interval, we can take f to be 1 over x. If x is equal to 0, we can take anything we want. Let's just say 0. This function, of course, is not continuous. It is not continuous. But it doesn't matter. We didn't say in the question, we didn't say that f should be continuous. So this function, of course, is not continuous. It looks like this. At 1, it's at 1, and then it goes to infinity. And then at 0, it is 0. And it is not continuous at 0. The point is that the function 1 over x, it is integrable on this interval from b to 1, where b is any number here. And the reason is that when you fix some number b, if you look at this area, it is a bounded area. Well, intuitively, it's clear, and algebraically, well, in terms of calculus, we can also compute that. 1 over x. What is the integral of 1 over x? Well, I expect you to know the answer. Can someone tell me what is the integral of 1 over x? Yes, ln of absolute value of x. But here, yeah, it's okay. But we don't need absolute value here, actually. You're right, because here x is positive. So, I mean, it's correct. Both of you are correct. So it's just ln of x from b to 1. Right? So it's going to be ln of 1 minus ln of b. But what is ln of 1? We know that. It's 0. So it's just going to be minus ln of b. And ln of b for a number b between 0 and 1, it's a finite number, of course. So for any b in this interval, this is a finite number, which means the function f is integrable on this interval b to 1. Okay. The second step, so the first step was to show f is integrable on interval b to 1. The second step is to show f is not integrable on the interval from 0 to 1. So integral of 1 over x dx, as you mentioned, when x is non-negative, is ln of x, right? So when we say from 0 to 1, because, well, the function ln diverges when x is converging to 0, we prefer to write it as integral from epsilon to 1 over x dx. And then we can take a limit and we can set epsilon to 0, where epsilon is a positive number. And this is going to be limit epsilon goes to 0 of, well, again, integral of 1 over x is ln of x when x is non-negative, from 1 to epsilon, which is equal to limit of ln of 1 minus ln of epsilon, where epsilon goes to 0, which is limit of minus limit of ln of epsilon, where epsilon goes to 0. Maybe it's better to keep minus inside because, well, we know minus ln of epsilon is ln of 1 over epsilon, and epsilon goes to 0. When epsilon goes to 0 and it's a positive number, 1 over epsilon goes to plus infinity. And when 1 over epsilon goes to plus infinity, its ln also goes to plus infinity. So if we take the limit diverges. It goes to infinity. Therefore, this integral here diverges. And therefore, this function 1 over x is not integrable on the interval 0, 1. So although it's integrable on any interval of the form b to 1, where b is positive, it's not integrable on the whole interval 0 to 1. Now, okay, and that's the answer to the question. Now, let's make the question slightly more special. So again, suppose we have a function from 0 to 1 to r, such that we know for any b between 0 and 1, the function f is integrable on this interval b to 1. Now, suppose f is also bounded. 1 over x was not bounded. Now we know f is also bounded. Does it imply f is integrable on the interval 0 to 1? Okay, think about this for a few more minutes. Again, either you should prove it is integrable, or find a counterexample to disprove it.
I think I got a counterexample.
Okay, what is that?
What about ln x?
ln
of x. Yeah, the
so,
function. Yeah. Yes,
okay.
because.
Okay, let's let the other people think too, and then we would check this if it's a counterexample or not. Good. Okay, so let's start with checking this example. First, we should see if, well, there are two conditions. One is that f should be integrable on the interval from b to 1, and the other one is f is bounded. First, let's see if ln of x is bounded on this interval. Well, of course, ln is not defined at 0. So if you want to define the function, you should just define it to have a value at 0. It doesn't matter. But is ln bounded on this interval? What is the limit of ln of x when x goes to 0? Negative infinity, yeah. Well, and therefore, it's not bounded. It's bounded above. Probably that's what you had in mind, which is correct. It's bounded above, but it's not bounded below. It goes to minus infinity. So it's bounded above by ln of 1, which is 0, but it's not bounded below. So this is not actually a counterexample. Okay. So let's try to prove it and see if we can, well, let's see if we fail or we really can prove it. So in order for a function f to be integrable, there are kind of different conditions. One is that there is a condition on the continuity of f. I mean, an integrable function is not necessarily continuous, but it can't have many discontinuous points. We know if f is integrable, f has at most countably many discontinuous points. And that's quite important. It means, well, of course, and we can have functions which they are not continuous like this, but they are integrable. We can compute the area under this graph of this function f, and it's integrable. But the point is that they can't have, well, if you look at the set of discontinuous points, yeah, it means by that, well, that's a kind of way of saying it, countably many. It means if you look at the set of discontinuous points of x, points of f, the set of points where f is not continuous at x, countably many is kind of a mathematical phrase for saying that this set has to be countable. Are you all familiar with the concept of countable and uncountable sets? I guess so. I think you've seen it in the first chapter. So it means either this set is finite, or if it's not finite, there is a bijection between this set and the set of natural numbers. Okay. Okay, so the first thing to prove, if we want to show f is integrable on the interval 0 to 1, the first thing to prove is to show, okay, so we are now trying to prove f is integrable on the set 0 to 1. So I should prove f, the set of discontinuous points of f, is at most countable. I should prove that. This is what I want to prove. I want to show f doesn't have many discontinuous points. Even if it has infinitely many discontinuous points, if the set of discontinuous points, this set is even infinite, it has to be a countable infinite. Okay. What I know, so this is what I want to prove. But what I know is that f is integrable on subsets of the form B to 1 for positive number B. Well, because f is integrable here, I know if I look at the discontinuous points of f, intersection this interval, because f is integrable there, this set is countable. Because I know f is integrable on this interval, right? So by the theorem, we know about discontinuous points of an integrable function. The set of discontinuity points of f, discontinuous point of f on this set, it has to be a countable set. Okay. On the other hand, if I look at all of the discontinuous points of f, it is union of discontinuous points of f intersection with b in 1, but rather where b is getting closer and closer to 0. But I can choose one kind of a specific b. I can take b to be 1 over n. So rather than, or maybe bn to be 1 over n. So I can look at these intervals 1 over n to 1. Okay, so I have this interval from 0 to 1. I can construct this interval. I can first look at from 1 over 2 to 1, and then from 1 over 3 to 1, and then from 1 over 4 to 1. As you can see, these intervals are getting closer and closer to the interval from 0 to 1. I would look at your example, okay? So when n is going to infinity, 1 over n is converging to 0. So if I look at the union of these sets for all natural numbers, when n goes to infinity, this thing is converging to 0. So I have this equality between these two sets. So does this equality make sense? Is it clear for everyone why this thing is correct? Maybe I should erase this. So on the left-hand side, we have every point x where f is discontinuous at that point on the interval from 0 to 1. On the right-hand side, I break this set to smaller pieces. I say first look at the points where f is discontinuous there, where the points are between 1 over 2 and 1. And then add the points which are f is discontinuous there, and they are between 1 over 3 and 1. And then add the discontinuous points between 1 over 4 and 1. And as you can see, where we are adding these small intervals, if we take union of all of them, when n goes to infinity, it converges to the set from 0 to 1. Okay, potentially we should add 0 to if f is discontinuous there, but it really doesn't matter. Now the point is that we know all these sets of this form. We know all of these sets are countable. Because we are assuming the function f is integrable on any set of the form b to 1 where b is positive. So f is integrable on the interval from 1 over n to 1. So the set of discontinuous points of f on this interval should be countable. And we have countable union of countable sets. And if you remember from the first chapter of the book, countable union of countable sets is countable. So what we have on the left-hand side is countable. Okay. So if we look at the function f from 0 to 1 to r, if we look at the set of points x where f is not continuous at x, this set is countable. That's the first thing to note. The second thing is that we should show this integral converges. This integral doesn't diverge to infinity. So in the previous example, f of x equals 1 over x, the integral goes to infinity. We should show this doesn't happen here, okay? So we had an extra assumption that f is bounded. So we had an assumption which it said f is bounded. It means there exists a number m where f of x is, its absolute value is less or equal than m for every x in this interval from 0 to 1. Okay, so if I look at the integral of f of x from 0 to 1, its absolute value is less than integral of absolute value of f of x. Maybe it's better to have dx here too. So that's always correct. This is always the correct inequality. The absolute value of integral is less or equal than integral of absolute value. And absolute value of f is less or equal than m. And since m is constant, we can bring m out of integral. So it would be just integral from 0 to 1 of dx, which is x. So it is x from 0 to 1. So it would be m times 1 minus 0, which is m. So this integral is bounded by m. If it's bounded, it means it's not going to diverge. It doesn't go to infinity. So it is bounded. It is bounded, and it had the set of discontinuous points of f is a countable set. It means f is integrable. Okay, there was a question. What about the function x equals 1 over 2 to the n? What is n? Oh, you're saying f, oh, let me write down this example. So there is a question which says, suppose f is equal to 0. Define f of x. Let's see if it's a counterexample or not. Is equal to 0 if x is of the form 1 over 2 to the n for some n, and it's 0 everywhere else. That means everywhere else. So for example, at 1, because 1 is equal to 1 over 2 to the 0, it should be 0. On 1 over 2, it's 0. On 1 over 4, it's 0. On 1 over 8, it's 0. On 1 over 16, it's 0, and etc. And everywhere else, on the complement of this set, it's equal to 1. So there are holes here, and at that hole, the value is 0. At these holes, the values are equal to 0. Okay, so well, let's see. Is it if it wants to be a counterexample, so your claim, do you think that it's a counterexample? Oh, you're asking if it's integrable or not. Yes, it is integrable. Well, integral of f of x dx from 0 to 1. As you can see, almost at every point, the value of the function is 1, right? There are only the set of points where the value of function value of f is not 1. This set is countable. And in some sense, they don't really matter in integral. So almost everywhere, the value of f is equal to 1. So the integral is just x from 1 to 0, and that's equal to 1. So the integral is 1. Yeah, good. Any question? Okay. Okay, so let's continue. For the second question, suppose f is a map from non-negative numbers, or say positive numbers, to the set of positive numbers. R plus means the real numbers, which are, they're positive. They're greater than 0. Where f is a monotone decreasing function. Okay. Also, suppose we know that integral of f of x dx from 0 to infinity is convergent. It converges, it's bounded. Prove there exists, prove the limit of x times f of x when x goes to infinity. Prove this limit exists and it is equal to 0. Okay, think about this question for a few minutes. Okay, so here we should prove it by, well, we use proof by contradiction. So I want to show this limit, this value x f of x, it goes to 0. First of all, note that we really know that f itself goes to 0 as x goes to infinity, because f is a positive function, and if it doesn't go to 0, this integral wouldn't be convergent. But this question is slightly harder because it's asking us to show this product x f of x goes to 0. Here we know f goes to 0 because it's integrable, it goes to 0. But on the other hand, x is going to infinity. So here we have multiplication of something which goes to 0 with something which goes to infinity. And we want to show this product goes to 0. Okay. So I use proof by contradiction. So what does it mean? Well, suppose the limit is, suppose it doesn't go to 0. It means there are numbers, there's a sequence of numbers like xn, there exists a sequence xn, where xn goes to infinity, where xn times f of xn, this number is, it's a positive number, it's greater or equal than epsilon. So it means there is a positive epsilon where this sequence xn, f of xn is greater or equal than epsilon. Why? Because if it's not true, if for any epsilon, this quantity x f of xn, if we can make it smaller than epsilon, for any epsilon, it means this quantity is going to 0. If it doesn't go to 0, it means there exists an epsilon, a positive epsilon. And a sequence of numbers, a sequence of points, xn, where xn times f of xn is greater or equal than epsilon, which means it doesn't go to 0. It always has some distance to 0. Okay. So in that case, f of xn is greater or equal than epsilon over xn. I just divide both sides by xn, and xn is a positive number. So it means integral of f of x, well, let me tell you this. Because f is monotone, after some point f of x should be greater or equal than epsilon x for x large enough. And therefore its integral should be greater or equal than integral of epsilon over x. But integral of epsilon over x is kind of like integral of 1 over x. It's integral of 1 over x times epsilon, and that's not convergent. Not convergent. It goes to infinity. Therefore, this integral goes to infinity. And that's contradiction because we assume this integral is bounded. Okay, I think we can solve another question. Question number 3, I guess. Find all the functions like f, continuous functions from the interval 0 to 1 to r, find all functions f from 0 to 1 to r, which they are continuous. And for some number a, where a is the number between 0 and 1, we have these three conditions. First, integral of f from 0 to 1 is 1. Second, integral of x times f of x dx equals a. And third, integral from 0 to 1 of x squared f of x dx equals a squared. For some constant a between 0 to 1, like 1 over 2 or something like that. Find all functions f which they satisfy these three properties. Let's recall a very important inequality, Cauchy-Schwarz. Inequality. For vectors in a Euclidean space like Rn, Cauchy-Schwarz inequality says if you have two vectors like u and v, their inner product u dot v is less or equal than the norm of u times the norm of v. So for example, in our case, where u and v are in Rn, I can write u as the set of numbers u1 up to un, and v as v1 up to vn. So their inner product is u1 v1 plus u2 v2 plus up to un vn. this number is less or equal than the norm of u, which is the square root of u1 squared plus u2 squared plus up to un squared, times the norm of v, which is v1 squared plus v2 squared up to vn squared. Now, an important thing is about the equality. So this is less or equal, but sometimes this less or equal actually is really equal. So u dot v, the inner product of u and v, is equal to norm of u times norm of v if and only if. Does anyone know the condition for these two to be equal? Yes. If there exists a number k, real number k, where one of them is k times the other one. So these two are two vectors. This is u, this is v. These two quantities, the inner product of u and v and the norm of u times norm of v, they're equal if and only if these two vectors, one of them is just a multiplication of a real number by another one. So for example, this is u and this is v. If k is positive. If k is negative, for example, it would be, v would be here. Okay, but they are kind of in the same direction. Well, the direction might be different, but either they're in the same direction or the opposite direction. One of them is a scalar times the other one. Okay, let's review Cauchy-Schwarz for functions. Here we have functions, say we have two functions f and g from an interval 0 to 1 to r. Cauchy-Schwarz again says their inner product is less or equal than their norm, the multiplication of the product of their norms. The inner product of two functions f and g is integral of f of x, g of x, dx from 0 to 1. And the norm is just simply the integral of the function squared. So here we get integral from 0 to 1, f of x, g of x, dx is less or equal than integral from 0 to 1 of f of x squared dx, well, the square root of that, times square root of integral 0 to 1 gx squared dx. Again, here we would have the equality if and only if one of these functions is k times the other one, or k a real number. Okay, now let's go back to our question. We were looking for functions f from 0 to 1 to r, continuous, where integral of f is 1, integral of xf is a, integral of x squared f is a squared. Okay, look at this quantity. Look at x times f of x. I can write it as integral of x times, well, say, maybe I should another assumption here. Let me think for a second. Yeah, let's suppose f is a non-negative function. So I can write it as square root of f times square root of f dx. Well, that kind of solves the problem. You know, well, f of x is of course equal to square root of f of x times square root of f of x when f is non-negative. So I just, instead of f, I write multiplication of square root of f times itself. Okay, now that kind of solves the problem because I can take this one to be, say, g of x, and I can take the second one, say this one, to be, say, h of x. Cauchy-Schwarz says integral of gh is less or equal than square root of integral of g squared times the square root of integral of h squared, right? Let's just write the same thing. So integral of x times f, which is integral of x times square root of f times the square root of f, is less or equal than square root of integral of x squared square root of f squared, which is f, times square root of integral of the second function squared, which would be just f, right? On the other hand, in the assumptions, we have integral of x times f equals a. This assumption says this integral equals a. And on the other hand, integral of x squared times f is a squared. So it would be square root of a squared. And integral of f is 1. So it's just 1. And square root of a squared is a. As we can see, a should be less or equal than a, which is equal. So we have the equality. And remember, we have equality only when one function here, g, is a number like k times the other function h. So in our case, x times square root of f of x should be a number like k times the other function, square root of f of x. Well, if f is not 0, we can cancel these two. It means x equals the constant number k. But that's contradiction. X is a variable. K is constant. They can't be equal. It's contradiction. Therefore, f has to be 0 everywhere. If it's not 0, we would just cancel square root of f of x from both sides, and it would imply x equals a constant number, which is wrong. But if f is 0 everywhere, what would be its integral? Its integral would be also 0, right? But we assume that its integral is 1. That's, again, a contradiction. So there is no function. There is no function f satisfying all 3 conditions. So there isn't any function like that. Is there any question? Okay, so if there is no question, that's it for today. Take care and goodbye.